Hello everyone, and thank you for watching my talk on quantifying the influence of an evolving mineral grain size on the characteristics of mantle flow. This is work I did together with René Gassmüller and Arushi Saxena, and so we wanted to know how does mineral grain size affect the mantle flow. And we know that the grain size is important for the viscosity in the diffusion creep regime, and also that most mantle convection models assume a constant grain size. So this is both because it's computationally challenging to include grain size evolution, but also because many parameters of grain size evolution are very uncertain. A few years ago, we did a study where we did include grain size evolution in global mantle convection models, and we found that it can have a big impact on mantle flow. But because these models were so expensive to run, we could not run a large parameter study. And so here we want to come back to this question: under which conditions it is justified to use a constant grain size, and if we allow the mineral grain size to evolve, how does that influence the mantle flow? But we will use a smaller example of the mantle below oceanic plates, which is a well understood system that is easier to model in a high resolution than global flow. And it's also a system where many observations are available. So, how does the mineral grain size change in the mantle? If nothing much is happening to the grains, then the grain size just tends to grow over time. But if grains are deformed, specifically in the dislocation creep regime, then this deformation breaks the grains apart and the grain size is reduced over time by a process called dynamic recrystallization. In addition, grain size can also change due to reactions, for example at phase transitions. But what I want to focus on are these two processes here on the left. We can also look at how this affects the viscosity. So if we plot the grain size on the horizontal axis and the viscosity on the vertical axis, grain growth and a larger grain size lead to a larger viscosity, whereas a smaller grain size leads to a smaller viscosity. And this also highlights a potential feedback mechanism. So if dynamic recrystallization reduces the grain size, the smaller grain size makes the mantle easier to deform, so more deformation may lead to more grain size reduction, and this can lead to a runaway. Now, the exact form of this relationship depends on a number of different parameters, and I want to focus on the uncertainty in two parameters. The first one is the balance between diffusion creep and dislocation creep. In the diffusion creep regime, the grain size influences the viscosity, so a small grain size leads to a low viscosity. Diffusion creep does not reduce the grain size if material is deformed, and so that means if we have only diffusion creep, then grains will tend to grow over time. In a dislocation creep regime, the viscosity depends on the strain rate, but it does not depend on the grain size. However, the deformation caused by dislocation creep reduces the mineral grain size. So in the Earth, we expect that both of these processes play a role and interact with each other, but that means it's very important where we are between these two processes. The other parameter I want to look at is the fraction of work that's being done by dislocation creep that actually goes into reducing the mineral grain size, rather than, for example, shear heating. And in the past, values of, for example, 10% have been used, but there's also the study of Rosell et al., who say that this is a good approximation in the lithosphere, but they looked at a lot of experimental data and say in the high temperatures below the base of the lithosphere, this work fraction may actually be much smaller. So in our models, we will vary those two sets of parameters. Now, we then want to compare our models to observations. One observation that we have is that we think dislocation creep should contribute to deformation in the asthenosphere because we have observations of seismic anisotropy. We also think that the viscosity profile in our model should fit viscosity profiles predicted from post-glacial rebound and the geoid, such as shown here. So the viscosity in the upper mantle should be between something like 10 to the 20 and 10 to the 21 Pascal seconds. And in addition, there may be a layer of low viscosity and strong deformation at the base of plates. Finally, we have observations of small-scale convection. So we know that for young plates, the half-space cooling model is a good fit to the thickness of plates, and so heat transport is mostly done by conduction. But if we go to older plates of around 70 million years or more in age, then the half-space cooling model overpredicts the thickness of the plates, and so we think that small-scale convection here may play a role in thinning the plate. So now let's have a look at the setup of these models. We run our models using the geodynamic modeling code Aspect, and we run 2D box models of the upper mantle. So our models have a height of 410 kilometers, and they are 4,000 kilometers wide. We have a mid-ocean ridge on the left side of the model. So we start with a plate age of 0, and then we apply a plate velocity of 5 centimeters per year at the top of the model. That means on the right, we have a plate age of 80 million years. And we allow inflow at the bottom and outflow on the right. Because we only model the upper mantle, we can use the olivine rheology of Hurd and Kolstad, and we use the grain size evolution parameters of Fall and Jackson. In terms of temperature, we start from the half-space cooling model, and we, as boundary conditions, we fix the temperature at the top, and everywhere where there is inflow, we prescribe this initial condition. We also start from a constant grain size, which is 5 millimeters, and everywhere where there's inflow, material flows in with a grain size of 5 millimeters. We can also have a look at how this grain size evolution looks like in the model. So the grain size flows in with 5 millimeters grain size, and then over time, in parts of the model that are hot and where there's little deformation, the grain size evolves to have larger grains. In parts of the model where there is strong deformation by dislocation creep, we have a smaller grain size. And the results that I will show are vertical profiles through the model where I show the viscosity. Let's first have a look at the model where we have a constant grain size and no grain size evolution. And here I show 3 different profiles for a model going from diffusion dominated, which is this black color, and then the models go towards more dislocation dominated in these lighter gray colors. All of these models have a high viscosity in the lithosphere, and then the viscosity decreases to the base of the plate. And then it depends on the deformation regime. If the models are in diffusion creep, which is not dependent on the strain rate, there is not a big increase in viscosity from the base of the plate to the base of the upper mantle. But in the models that are in dislocation creep regime, the strong deformation at the base of the lithosphere leads to a lower viscosity, and then the viscosity increases further down where there is less deformation. We can also look at how these profiles change for younger and older plate ages. So in the center of the model, we have 40 million years. If we look at the younger plate or at the older plate, we see that these models are very similar, and only the base of the plate, so the depth of the base of the plate increases with the age of the plate. And this is where we have the lowest viscosity. And this is also what we expect. So now, as a next step, let's compare these models with a constant grain size to models with an evolving grain size. These again are different models that go from diffusion dominated to dislocation dominated. First, we can see that where these models have the lowest viscosity, the base of the plate happens in a similar depth and also at a similar viscosity. What's different is that in the models with an evolving grain size, even the ones that are diffusion dominated, they increase in viscosity from the base of the plate further down. And this is because the diffusion creep is grain size dependent. So where there's a lot of deformation at the base of plate, we have a smaller grain size, and further down where there's less deformation, we have a larger grain size, increasing the viscosity. We can also do a more systematic comparison of these different models with and without grain size evolution. So what I show here are different viscosity profiles for models that are all in the dislocation creep regime, but they have different work fractions of dislocation creep reducing the grain size. And what we see here is that in the dislocation creep regime, all of these viscosity profiles are very similar. So there's not a big difference between them. If we go further from dislocation dominated to a viscosity where both diffusion and dislocation creep play a role, then we can see that this work fraction now has a bigger influence. So if we go from red colors to blue colors, this location creep has a bigger potential to decrease the grain size. And so the further we go from red to blue, the smaller the grain size is, and so the smaller the viscosity becomes. But here we could still say these models all look very similar, and grain size evolution actually does not play such a big role. Now, if we go to even further influence of the fusion creep, we now see that the model, the blue one, which has the work fraction of 10%, actually looks very different from the other models. So what's going on here? First, we see that the viscosity is much lower in this model, and that the lowest viscosity is also at the shallower depth. So it looks like the plate is thinner. So let's have a look at the strain rate in these different models. So the model of 10%, 1%, and 0.1% work fraction. That's what's shown here in this animation. So let's start the animation. And we see that in the model of the small work fraction, that basically is in steady state from the start, and the deformation stays as it is. But in the model at the bottom, right from the start, we have a lot of like changing behavior, and there's a lot of small scale convection. First, that thins the plate, and also the deformation decreases the grain size and reduces the viscosity. But we also see that the small scale convection already happens at around like 30 or 40 million years. So this is younger than what we think it should start from the observations. But if we look at the model in the center, which has a work fraction of around 1%, we see that in the beginning, there's not much going on, but then at some time, there's some convective behavior that starts here, and we actually do get small scale convection too, and it starts at an age of around 60 or 65 million years. So this would be closer to what we would expect from the observations. So to summarize these results, we have seen that grain size evolution is important in models that have a balance of the fusion and dislocation creep. If we are dominantly in the dislocation creep regime, then grain size evolution would not have a big influence. In addition, if the work fraction that goes into reducing the grain size is small, such as predicted, for example, by the model of Rosell et al., then the grain size evolution does not have a strong influence on the flow in the upper mantle. However, we find that if we are in the balance between diffusion and dislocation creep, and if we have a larger work fraction of around 1%, then we find the best fit for where the onset of small scale convection should be. But we have to keep in mind that there are a number of things where our model only approximate what happens in the real Earth. For example, there are still a lot of uncertainties in other model parameters, and also we have much less thermal and thermochemical heterogeneity in our models than in the real Earth. So what we want to do in the future, we want to do a more detailed comparison of our models to the observations, and we also want to go back to the global scale. So this work is part of a larger project where we want to run high resolution models based on seismic tomography and then make these models available to the community. So if you're interested in that, you can go to our website, integrated-earth.github.io. And then the part of the model that concerns the grain size evolution, what we want to do is we have a global model where we prescribe weak plate boundaries to get a realistic mantle flow, and then infer the temperature from seismic tomography models. And the relation of getting the temperature from seismic velocity actually depends on the mineral grain size. So if we can predict the mineral grain size in our models, that could help us to actually better understand what the temperature distribution in the Earth is. Thank you.